Why the hyperbola? Our earlier videos exhibit the hyperbolic production functions, unique enabling of a closed-form solution to economics' polynomial factoring problem, as well as their critical role in the computation of efficient prices in a dynamic context. And, consulting our demonstration that hyperbolic production and utility coefficients present attractively consistent time series, SFEcon persists in its conviction that hyperbolic expressions of technical indifference deserve to be privileged above the available alternatives. This video continues our argument in terms of the hyperbolic form's place among naturally occurring phenomena of all descriptions, which aligns with our guiding premise that valuation is a universal phenomenon, of which the familiar economic system is but one instance. Insofar as we can determine, the economics profession's present uses for hyperbolic descriptions of technical indifference are all but non-existent, the uses of which we are aware being limited to bemused asides in discussions of price elasticity. Here it is observed that hyperbolic demand schedules induce elasticity computations that resolve to unity throughout the domain of demand. SFEcon's demand schedules, being based on hyperbolic utility functions, are themselves hyperbolic, thereby altogether trivializing the elasticity notion. SFEcon finds this to be no great loss, because our system works out the dynamics of every variable, as they follow from the disturbance of any variable, anywhere in the web of exchange. SFEcon's emulators make reference to hyperbolic forms for both the supply of and the demand for economic goods. Markets for economic goods, which control these emulators, are therefore computed by recursive numerical integrations, arriving at the areas beneath hyperbolic functions. Thus, control of the SFEcon system is traced to the natural logarithm, which is also defined by the area under a hyperbola, as shown. Natural logarithms are fundamental to the family of transcendental functions, having a peculiar relation to the West's characteristically dynamic scientific worldview. It might be fairly said that any differential system whose solutions are known to us can be solved in terms of transcendental functions. Had transcendental functions never been devised, comparatively few differential systems would now be solved, and it is difficult to conjure even one naturally occurring dynamic phenomena among the remainder of the solved problems. The number E is also a creature of the hyperbola, and it is essential to the understanding of dynamic phenomena by way of the integral calculus. Delay mechanism, the most elementary of naturally occurring dynamic machines, describe exponential decay, as of heat, radioactivity, or electrical charge. Somewhat more sophisticated notions of delay are used in common business practice and in SFEcon to account for the deterioration of an unreplenished or unmaintained physical asset. Exponential growth also describes the pattern of increase for unbounded biological systems as well as for unserviced financial positions. So considered, it should be difficult to imagine any expression of economic dynamics via the integral calculus that does not somehow, if only unconsciously, center on the hyperbolic form. That is, if the investigator first resolves to discover economic causality among naturally occurring phenomena. If states of nature are arrived at by dynamic processes of accumulation and development, then these processes must follow patterns that are both simple and repeatable as systems grow in the dimensions of time and space. Simple patterns are essential because they are the least likely to be corrupted by repetition. The golden mean is foremost among the simple patterns to be observed everywhere in nature. The figure showing has this expressed in the lengths of a certain rectangle's sides. This rectangle is peculiar in that sectioning out of squares from the rectangle leaves a smaller rectangle having the same proportions as the larger. This pattern is simple, yet it can be grown endlessly in space without deviation from the simple rule creating it. The golden mean's geometry often finds expression in nature through the logarithmic spiral, The figure showing derives this form by its inscription in the rectangle shown just now. This figure depicts a chambered nautilus as an example of the log spiral's occurrence in a natural system. Here the animal's growth has left a spatial residual of the rule governing its temporal development. The next figure shows this same rule operating on the vastly different scale of a solar system. Antique cultures, where they have achieved sufficient persistence and development to have left a trace in history, have all discovered nature's use of the log spiral. They have shaped their art and their technologies to accord with and engage the natural advantages of this formula for repeatable development in space and time. The Viking Longboat, one of history's premier technologies for economic development, is suffused with forms exhibiting proportions of the natural logarithm. These technologies are often finished with designs proclaiming their underlying pattern, as shown in the carved prow presented here. Ancient wisdom might be further extended in this direction if the economist's notion of a general optimum is discovered as the pattern around which economic dynamics are stabilized. Alan Kerman and Werner Hildenbrand expressed economics' frustration with the problem of deriving such a pattern from accepted economic causality. One would like that the equilibrium should be a resting point of an economically plausible price adjustment process. Nevertheless, to model such an adjustment process in a realistic way is extremely difficult, and till now, nobody has succeeded in doing it satisfactorily. If we are going to model economic adjustment as progress toward the optimum, then such a model would logically operate on a generator of elementary forms that can grow in time and space by replication of its simple rules.